In section 8.3, we're going to look at collisions a little closer. Our objectives here are to differentiate between elastic and inelastic collisions, basically what each of those types of collisions would look like and what that means, and also to use conservation of momentum and energy to solve some collision problems. There's essentially two types of collisions, and when we look at collisions a little more closely, they might look a little different than what you might initially imagine. Now, on a macroscopic level, collisions might look like car crashes or a couple of billiard balls running into each other. They might look something like we see in this picture here. But if we were to really look at collisions closely, we might realize that really all matter is made up of atoms. All atoms have electrons on the outsides of those atoms, and those electrons are all going to repel each other. So really, when we start to look at collisions on a microscopic level, we would realize that two charges with the same sign would never really touch and run into each other or stick together, but they'd almost be sort of these glancing collisions with one going this way and one going that way. So just kind of looking at what collisions actually look like. We know that momentum in an isolated system is conserved, and that would include collisions as well. So momentum is going to be conserved in any type of collision. Whether we look at it at the macroscopic level and just sort of envision two things coming together like a car or a billiard ball, or whether we look at it on the microscopic level, this is true. Momentum is going to be conserved. But what about kinetic energy? In general, kinetic energy is not conserved in a collision. Imagine maybe a rubber ball that's colliding with the floor, like you're taking your super ball and bouncing it against the ground and it's kind of going up and down. Now, what forms of energy are present upon the collision between that ball and the floor? Well, the ball is going to be deformed a little bit. As soon as it hits the floor, that side of the ball is going to flatten a little bit. In fact, that's what causes the rebound. So there's some energy that went into deforming the ball. That ball, upon hitting the floor, is going to maybe make a little bit of sound. Those mechanical waves also require some energy to create them. And even a little bit of heat. The floor and the ball will probably be a little bit warmer upon that collision. So the kinetic energy that this ball went into the collision with is going to be lost to some other forms, like sound, heat, and deformation. An inelastic collision is one where the kinetic energy is not conserved. This is when two objects collide and stick together to create really a maximum possible transfer of kinetic energy to other energy forms, and that would now be called a perfectly inelastic collision. So anytime we have two things that are colliding and then sticking together upon that collision, we would call that a perfectly inelastic collision, and that's where the maximum amount of kinetic energy is lost or transferred to other forms. This might be two cars that are crashing and becoming entangled as one. It might be a bullet that's hitting a target and then becoming lodged inside of that target. If we were to conserve momentum, we would see that that momentum equation for two objects that are colliding would look like finding the momentum of object 1, which is its mv, the momentum of object 2, which is its mv, and that would all be the total initial momentum. The final momentum would now be the total mass of the two objects stuck together multiplied by a final velocity. Now let's move on to an elastic collision. An elastic collision is one where the kinetic energy is conserved. Now remember, momentum still is conserved also, but here we have both being conserved, both momentum and kinetic energy. An example of this would be something more like billiard balls, or maybe even one of those Newtonian demonstrators that has the multiple spheres kind of hanging from strings. And what you notice about something like this is that when one ball kind of swings in and strikes the other one, what you find is that all of that momentum and energy is conserved so that the last ball kind of swings back out with the exact same amount of energy. So again, you're looking at an example where kinetic energy is conserved. Billiard balls tend to kind of do this too. You might have, the cue ball coming into the 8 ball. And when these two collide, all of a sudden the 8 ball takes off and is moving with some velocity, and the cue ball is just kind of sitting there at rest. These are examples where you kind of trade off that total momentum and energy is being conserved. Now, in reality, pool balls or even the Newtonian demonstrator, those would not be perfectly elastic collisions. Why would that be so? Of course, it's because some energy goes into other things. Remember, kinetic energy being conserved is the definition of a perfectly elastic collision. So when you have these spheres sort of running into each other, or the pool balls running into each other, some energy has gone into creating some sound and a little bit of heat. In fact, if pool balls had perfectly elastic collisions, the opening break in a pool game would actually be perfectly silent. Now, atomic particles are things that do have truly elastic collisions. Those are more of those glancing collisions where one's kind of coming in one way and the other's coming in the other way. And these two things never really touch each other, which means that they don't have the possibility of generating heat or sound. Now, perfectly elastic or inelastic collisions are really extreme or limiting cases, and most collisions fall in between, but we'll simplify problems to kind of fall into one of those categories. So we will typically look at a problem and classify it as either elastic, where we can conserve both kinetic energy and momentum, or inelastic, where momentum would be the only thing that's conserved. It is important to recognize that momentum is conserved in all collisions, but kinetic energy would only be conserved in those elastic collisions. So in general, when you're solving a problem, you want to draw a picture, get a feeling of what's going on in that problem, what kind of collision you have, determine if that system is isolated, and if it is, categorize it as an elastic or an inelastic collision to determine if you can conserve momentum or momentum and energy. Finally, set up your appropriate equations and solve, and check and make sure that your answer makes sense. Now, for elastic collisions, since both momentum and kinetic energy are conserved, typical problems involving elastic collisions would actually have two unknown quantities, the final velocities of both objects that are in that collision. And it's okay to have two unknowns because we have two equations that we can set up. Remember, for an elastic collision, we can conserve momentum, where the momentum coming in initially is equal to the momentum coming out, and we can conserve kinetic energy. So the 1/2 mv squared initially is going to have to be equal to the total 1/2 mv squareds of each of the objects in the end as well. Now, as we look at setting up these two equations, they really are two equations with two unknowns that can be solved simultaneously, and if those two unknowns that you're solving for are always the final velocities of the two objects, we can really just simplify those things and show you what those equations would actually be. Now, sometimes this is helpful so that you don't actually have to go through the solving of those two simultaneous equations. It saves on a little bit of the algebra work. So here you have some equations for the final velocity of object 1 and the final velocity of object 2, again, based on these being elastic collisions. So remember, when you're working with these equations, number one, be sure that you're putting in the appropriate signs, meaning that you choose a direction to be positive and a direction to be negative. If one direction is negative, make sure you're sticking in the negative signs in for those velocities. And number two, always remember that these equations here are not necessarily something to be memorized. What you would really memorize is the idea that you can conserve momentum in any collision and that you can conserve kinetic energy in an elastic collision. But if you're going to use these equations that we have simplified here, do remember that they can only be used for those one-dimensional elastic collisions, basically meaning that we are along a given plane. So two objects are coming in maybe along a straight line and having a collision. With two-dimensional collisions, you would not be able to use these. We'll look at two-dimensional collisions in the next section. So let's just look at a couple of special cases with these equations before we are finished with this section here. What would happen if M1 and M2 were the same size? So basically, when we take M1 minus M2 in this equation here, this whole thing would turn out to be a 0. And what we're recognizing here then is that if, again, they're the same size, this would essentially come out to be a 1. And what we're recognizing is that if the two objects were the same size, then the final velocities would really just be trading velocities. The final velocity of one would be equal to whatever initial velocity object 2 came in with. And the final velocity of object 2 would really just be equal to the initial velocity of object 1. Again, very much like a Newtonian demonstrator. Whichever speed and velocity you have coming in, you trade that off with the next couple of objects and they leave with that exact same velocity. If you had M1 as a very, very large object compared to M2, then what we'd see here is that, let me erase what we have on here right now. What we'd find happening here is that M1 is really, really big. And so when we do that, we'd find that if M1 was really huge, then object 1 doesn't really change its speed very much. So basically, this term ends up being about a 1, so that the final velocity of object 1 is about equal to the initial velocity of object 1. It really comes and goes with almost the exact same velocity. If it was a really large, maybe a bowling ball running into a tiny little ping pong ball, and you have this thing kind of coming into this collision, the bowling ball is going to keep chugging along pretty much with its same velocity when it runs into that tiny little ping pong ball. And we can see that happening with our equations that we have simplified over here. That those would essentially simplify to about a 1, and the big object would kind of just keep moving at its same speed. What we'd also find is that the second object would move away with about twice the speed. So when we look at the final velocity of object 2, with M1 being very large, it would really move away with about twice the velocity that M1 came in with. The last scenario that we have here is what if M2 was much, much larger and maybe even initially at rest. If M2 was initially at rest, what we would be looking at here is that the initial velocity of object 2 would essentially be a 0. So this whole term would sort of go away. And what you'd find that if M2 was really, really large, then that object would kind of just bounce off of the other one. So this might be a scenario more like where you've got the bowling ball as mass M2 and a tiny little ping pong ball kind of coming in at it where the bowling ball was at rest initially. Now what you'd really see happening here is that the ping pong ball would kind of just bounce off of this thing and sort of rebound back the other way. Again, we just see those same that same understanding emerging from the equations itself, that we know that these are things to be true if we were to envision these large and small masses colliding, or maybe equal masses colliding, what should happen with these objects. And what we recognize is that our simplification in these equations is in fact showing exactly what we would expect to happen.